Okay. For your written test number 1, I presume you have already read the guide, right? About the policy. And I just want to remind you, you really have to make sure these two accounts work. Otherwise, you will be wasting time fixing them on the test day. Try to do them before the test. You still have today until Friday. So don't really try Monday. That'll be maybe too late, right? Just try earlier. Your EECS account, your passport account, make sure they both work for the login. And about the practice question, I'll show to you very quickly. So I just released them just before today's class. If you go to the E-class, under written tests over here, there's some example question for you. Right? You can take a look. And of course, you should really still prioritize your time for studying at the actual coverage for the test. That would be more important. These questions might help, but they are not complete. And there is a survey on the E-class just about whether or not you're interested. If you find that you need a review session, I haven't got many responses so far, so I presume maybe you guys are not so interested. But anyway, so I will try to make a decision soon. If you're interested, fill out the survey as soon as you can, so I can make a decision. If no, then you're still very welcome to come to my office hour instead. Let me know. Okay. Okay, so that's about the written test 1. And for your assignment number 1, it will be due very soon, right? You can check the deadline. And if you want any help, office hour or the TAs. Just for today, the office hour will be over Zoom. I won't be on campus today, but if you dial in over Zoom, I'll be more than happy to help you. You can share a screen, you can talk about any issue you want about the course. All right. Any question about written test 1? Anything? We good? All right, so let's now continue. So last time, let's do a quick recap about what we did last time. So last time, let me just go back to the way we were in the beginning. So last time, we spoke about 2 kinds of nested loop to really figure out the asymptotic upper bound. Not really to count precisely the number of primitive operations, but just to approximate. So one of the practice questions I gave to you, they actually require you to count precisely the number of primitive operations. So take a look and make sure you do the exercise before you go through the solution video for that particular question. We'll talk about this one here, and also we talk about the more challenging one over here. And the critical thing is you ought to know how to derive the patterns on the loop counters. That's the critical thing you want to make sure you can do. And you definitely might get something similar to that in the actual test or even the exam later. Right? If you still want to speak to me about it, you still have today and tomorrow. And we spoke about the arrays, basic operations. Hopefully we can also move on to linked list today, at least for the introduction. It's actually a more fun subject than arrays. You maybe are very tired of working with arrays for so many courses already, but we definitely see something new. Right, we'll talk about insertion or deletion from the array will be expensive, it's linear time, right? Look at the procedure and make sure you can derive the asymptotic upper bound if I give you something similar. And we talk about sorting. Sorting is a very classic problem for computer science or software engineering. You ought to know some terminology. So we talk about sorted in decreasing versus increasing versus non-descending versus non-ascending. We'll talk about all these. Make sure if I give you any one of them, you would know what they really mean formally. Especially like what should be the relationship between 2 elements in the array. That's really important to know. All right, that's what we covered up to last time. Any question about clarification, anything? Alrighty, let's now talk about something new. As I promised, I'm going to show to you insertion sort and selection sort. So think about this is more like a case study on the arrays. So both of the sorting strategy we're going to see, they will be implemented by using array. Theoretically, you can also use linked list. It's possible. I'll leave that as an exercise for you once we finish discussing the linked list. But for now, let's focus on arrays. The roadmap is going to be like this. We're going to present to you intuitively how these 2 sorting algorithms work. They're actually quite straightforward. And then we'll try to see, given just an intuitive sketch, can you already derive the big O from that? We'll try together. And then I'm going to look at the actual Java code. And we're going to do some exercises on deriving the asymptotic upper bound, which we did last time for nested loop. And then there will be some important exercise for you, which is to really trace the Java code to see exactly how they work. And I wouldn't really spend the time in class, but I'll give you a little bit of highlights about what you should really look into. And there are some videos, optional, if you really find the need to really go through the tracing yourself, rather than just doing it on your own. You can also look at the video. I'll leave that to you. Of course, what we talk about today wouldn't be covered in the written test 1, thinking the long term. They might be covered in written test 2 or the exam. All right, that's a roadmap for today. And hopefully we can finish that and then we'll move on to linked list. All right, so we're going to focus on discussing these two algorithms and talk about their time complexity. Of course, upper bounds. We never talk about lower bound. Selection sort and insertion sort. Okay, let's now talk about some intuitive idea. Because in case you ever forget about how insertion sort and selection sort work, you don't really just look at the code to remind yourself about the details. You want to think about how do they work at a high level. Okay, let's start with the selection sort. You want to, so the idea will be, let me go over some bullet point with you and then I'll draw. We want to maintain the so-called sorted portion. Initially, this sorted portion is empty. The idea will be we want to run some loop. Eventually, we want to grow the sorted portion to cover the entire array. Okay, that's the idea. From left to right in the array, we're going to keep selecting and keep inserting the minimum element from the unsorted portion to the end of the sorted portion, so it remains sorted. That's a one-line summary, like a one-sentence summary for selection sort. All right, let's take a look to see how that works. All right, so here is the principle. Let me just repeat again. You want to keep selecting the minimum. Given an array, I'm pretty sure you know how to write a loop to select the minimum, right? Just go over from the beginning until the end and select the minimum. And then you want to select it from the unsorted portion. What's going to happen is, when I illustrate visually, you want to watch out exactly how the unsorted portion is going to shrink by each iteration. Accordingly, how the sorted portion is going to grow in each iteration. That's the main intuitive idea you want to get. The same idea will go also for insertion sort. All right? And every time, if you select the minimum from the unsorted portion, you're going to grow the sorted portion by appending that minimum to the end. All right? So there are two operations you can already see. One is about selecting. Second one will be appending. Think to yourself, which one is cheaper than the other? Okay, think about it, and then we'll get there. Okay? Let's say we have an array over here, 3, 1, 4, 2. Let's say we want to sort it in the increasing order. Eventually, we want to get to 1, 2, 3, 4. Let's say eventually. At the moment, it's completely unsorted. So that's why I'm using the red over here to say the entire array is considered unsorted. What we want to do is eventually, we want to turn the entire array to be green. So it's entirely sorted. That's the goal. All right? Let's now take a look. For the first iteration, let me just duplicate an array over here. What's going to happen is, for the first iteration, we're going to select a minimum from, because we're actually going to cover, we're going to select from the unsorted portion, which is going to be from index 0 to index 3. I'll just say from indices 0 to 3. In this case, which one is the minimum? This one. Agree? Okay. Think about, in theory, what will be the cost for selecting the minimum? Are we always this lucky to find the minimum right away? Not really, right? Okay, think about it, right? So here, 1 is here, right? So what I'm going to do is we're going to somehow append the selected minimum to the end of the sorted portion. Right now, the sorted portion, think about here, the sorted portion is simply just empty. Think about when started, sorted portion is empty. Okay? So what we're going to do is we're going to put 1 to be the sorted portion. So now the sorted portion will effectively grow to this one here. And then, what about the unsorted portion? is going to contain the remaining elements, which would be 3, 4, and 2. So 3, 4, and 2. So these remain to be unsorted. Are we okay so far? So we talk about for each iteration, you're going to keep selecting the minimum from the unsorted portion and grow the sorted portion by appending that to the end. Right? We're going to keep doing this until the green portion here that's sorted is going to cover the entire array. That's called selection sort. Let's do a little bit further so you can get more idea. In the first iteration, this will be the minimum. So I'll just say array at index 1. And then we're going to append that particular elements to over here, right? What about the second iteration? For the second iteration, so now, how do we select the minimum? We should select the minimum from index 1 to index 3, the unsorted portion, which would be 2, all right? It's going to be this number over here, and then at index 3. So from here to here, we have to select the minimum from indices 1 to 3. In this case, it's going to give us array at index 3. All right? 1 happens to be the end of the sorted portion. So now we're going to append 2 to the end. So now we actually got the sorted portion grown by 1 element. What about unsorted portion? Well, what do we have remaining? 3 and 4. 3 and 4. So that is unsorted. So visually, you can see very clearly the following. By moving 1 iteration, the unsorted portion is going to shrink by 1 element. Symmetrically, the sorted portion is going to be grown by 1 element. That's a critical thing. All right? Let's continue. And then we can work out the running time already. Okay? Let's take a look. So we got another one here. So we're going to select a minimum from the unsorted portion, which is 3. All right? So select the minimum. But for this time, I'll just tell you which is the minimum, which is index 2, which is 3. Index 2. In that way, we already got 1 and 2. Now we append this one to the end. And then we got 1, 2, 3, right? And then we got 4. All right? One final iteration, right? We still have to select. You might be wondering, well, if this is already 1 element, shouldn't we just append it directly? Yes, I agree. But let's just get the execution done consistently. But when you see the algorithm, in Java itself may have a little bit difference in terms of implementation detail. But I would say it's more important for you to understand what's happening here. All right? Final iteration will be, let me append it again. Okay. There we go. That will be the final one. And the final one is going to, again, select the minimum, which is going to be 4 at index 3. Well, which will be array at index 3. All right? So it's going to be 1, 2, 3, and then we're going to append this minimum to the end. So now, effectively, we got every element in the array belongs to the green area, the sorted portion. That's selection sort. You can see for each iteration, I try to do 2 operations. Number 1, selecting the minimum from the unsorted portion. Number 2, I try to append whatever the selected minimum was, append it to the end to grow the sorted portion. We got 2 operations. And given this information, we can already work out the running time. Can you guys imagine how? And this nicely corresponds to some pattern we spoke about last time. Any insights you want to share before I talk about it? Just hold on. Anyone at the back? You guys are always quiet. Don't be shy. Anyone want to share? It's okay to be wrong. This is kind of the technique you want to have from this course. You don't necessarily have to see the actual Java code to see the for loop syntax to work out the running time. You ought to say, given the abstract idea on the sketch of the paper, you should already work out what the asymptotic bound is. Yes, please. Sorry, say it again. The number of iterations will be how many? In this case, you have 4, which correspond to the size of the array. Yes, input size. Very good. And then? Big of n. OK, that's very good start. So I agree with you. We do have n iterations to go. Let's write it down. Facts number 1. N iterations. Or let me be a little bit more precise. Need to choose the minimum n times. All right? Everybody follow? So you can see here, in the case where we got input of size 4, we have to select the minimum 1, 2, 3, and 4. So the number of times you have to choose the minimum depends on how many elements you have in the array conceptually. Right? That's really important. But I wouldn't say the running time overall is big O of n, because choosing a minimum is not really constant, is it? That's what you're missing. Ferrets. The final answer should be big of n squared, but can you just elaborate on how you derive it? That'll be more useful. Yeah. We definitely have to account for appending time. But in this case, whenever you want to append something to the end, it's a constant operation. That one there can somehow be dropped. It's a lower term. I think what we are missing here is about how we can choose the minimum. That's really missing. I would like to know what's going to be the pattern. Is it always going to be n? Let me, guys, I'm glad you guys want to contribute. Let me just say one more thing, and then I'll take your thought. What you want to think about is, the first time I try to select the minimum, I got the entire array for me to select. The second time I want to select the minimum, I'm not selecting exactly that entire array. I'm only selecting what's in the unsorted portion. And then the search space for the minimum actually shrinks every time. Would that make the overall selecting the minimum running time be big O of n or something else? Right? That's what you want to think about. Okay, I saw many hands raised. Do you guys still want to? Yeah, go ahead, please. Aha, I like that, triangular. I agree. Okay, if you, yeah, go ahead. Yeah. Absolutely. Absolutely. Yeah, asymptotically, there's no difference, but I see what you mean, because somehow we are. Okay, the selection process indeed gets more, let's say, more and more cheaper, indeed. But ultimately, when you add up the numbers together, it will still be n squared. Yes, very good. All right, guys, if you don't mind, let me just start walking you about the logic here. So guys, let me emphasize again, I'm not trying to be too hard on you, right? That's something you really want to get from this course. Let me repeat. You don't really need the concrete piece of code that's already implemented to figure out the running time. What's more valuable for you is to say, I have certain idea. I got maybe 5 ideas about how to implement an algorithm. You ought to just sketch the critical steps on a piece of paper. Based on those, like what I'm doing here, you should be able to derive the running time already. That's really a valuable part about this course. We do coding. At the same time, we also try to do abstract analysis. All right, let me talk about it. Let's now be a little bit more abstract here. If I start with an initial array, okay, size n, all right? Oh, to be more precise, how about this? So here, let's say we got n elements. So think about the cost of selecting the minimum would be n. Would you agree? Because in the worst case, you have to scan through the entire array to find out the minimum. Actually, you always have to to really scan through the entire array to find the minimum. That's the cost. What about once you find the minimum, let's say over here, how do you append it to the end of the sorted portion? You can do some swap, right, for the array indices. That's something you will see in the algorithm. And to really append, it will just be a cost of 1. So pay attention to these two numbers over here, n and also 1. All right? That'll be for the first iteration. And when you actually go to the resulting array in the first iteration, let's see over here. Okay, let me be very precise. Give me a moment. So that means we got this part over here, and also what we got 1 green, right? Like that. So to really go from the initial array to that one there, okay, so that's really what I meant to put. And we're going to do one more. So this is just one element here, and we got n minus 1 elements in the unsorted portion. Let me finish this, and I'll take a question, if you don't mind. And let's now try to see what's going to happen in the next iteration. In the next iteration, our goal is to really find the minimum inside this unsorted portion. That's cost will be n minus 1. Okay, from here to here, it's going to be selecting the minimum. It will be n minus 1. What about appending? Let's say, for example, if you happen to choose the minimum to be here, all you got to do is to swap this element here with the element here. By swapping, you know how to do it, right? It's also constant time. So append is also 1, all right? So that means we got one elements, and remaining 2 will be n minus 2. So we got n minus 2, and here we got 2 elements over here. Right? How can we generalize this? So there are 2 parts over here. One part is about the selection. The other part is about the appending. Let's now do that. Big O of, all right? Let's talk about appending. Each time, for each iteration, we're going to spend only constant time on appending. And how many iterations do we have? N. So you can think about it's n times 1. So here, n over here will be the number of appending. All right, and then plus, and here is our nice pattern. Initially, selecting the minimum from the entire array is n. Next one, because the area for the unsorted elements shrunk. So that means it's n minus 1. So we're going to do something like this. N plus n minus 1 plus all the way to just 1. When you got only one element to choose the minimum from. All right? Over here, and we know very well, this is the sum of the arithmetic sequence over here. Right? This part here is simply n plus 1 times n divided by 2. Why? Beginning turn, n turn. How many turns do we have? N turns. So that's why divided by 2. Right? And if you do the math, it's going to be, you can simplify that if you want, but I can tell you that I'll leave this part here to be question mark, meaning that you have to simplify this. Right? I'll let you do it. But ultimately, you will see that the highest term will be big O of n squared. Right? Because you can see this part here, you already got n times n, which will be n squared. That one is going to dominate the appending operation, which is linear. Right? So the final answer is big O of n squared. For selection sort, it's a quadratic sort. Yes, question? Yes, please.
So looking at the first iteration, there's one thing that's confusing me a little bit, is that I understand that finding the minimum is n, and I understand that appending the minimum to the next array is 1. But my question is, when it comes to copying the remaining n minus 1 elements that weren't the minimum to that new array, wouldn't that be n minus 1?
Very good, very good. Let me repeat again. So the question was how appending works exactly. Okay? Appending. Let's say here, for the first iteration, we already know that the minimum is at index 1. Our idea is we want to insert it into the sorted portion currently empty so that it becomes at index 0. We don't need to do any shift. All we do is we just try to swap these two elements. Only a swap operation is needed. So once we swap, you can see what 3 goes to here, 1 goes to here. After that, this part here still remain unsorted. We don't care how much more unsorted or how much less unsorted it is. We only try to put this guy here into here. Let me do one more, okay? When we select the minimum from this unsorted portion is this one here. All we want is we want to insert this to the end of the sorted portion, which should be index 1. So all we do is swap these two elements. When you do swapping, it's only constant time.
But then should the next iteration be 1, 2, 4, 3 instead of 1, 2, 3, 4? If you're just swapping the 2 and 3?
Yeah, it could be, yeah. It could be maybe 4, 3, yeah. Don't worry too much about it. It's more implementation detail. For now, I just want to give you the conceptual idea. Indeed, when you look at the actual Java code, it will actually do some very smart swapping. So you don't really need to care about how unsorted this area is. We might even change the order of elements when we do the unsorted, depending on how you implement it, but that's okay. As long as for each iteration, you try to grow the size of the sorted portion by 1, you're fine. Okay, that's a critical idea. Yes? Okay, in this case, you don't really want to create a new array because I can mention this term. That's something I plan to mention a little bit later anyway. Okay, this is something called in-place sorting. Okay. Okay, by definition, that means the sorting procedure does not require how about this? Let me just say a little bit more straightforwardly. Beg your pardon. The sorting procedure operates directly on the original input array or input collection. Let's say input array. Without any help, some intermediate structure. So sometimes people, when they actually want to do sorting, let's say if you got a very large array, in that case, you don't really want to waste any space by creating any intermediate space, like an array. All you want to do is you're just swapping things around in this original array. Okay, there's some space concern over here. All right, so this selection sort, without even looking at the Java code, is n squared. Any questions? Right, let me recap. To do selection sort, the expensive operation for each iteration will be selecting the minimum. And the cheap operation is about appending or to grow the size of the sorted portion. For insertion sort, it will be the exact opposite. Selecting the member to really grow the size of the sorted portion will be the cheap one. But to actually grow this sorted portion itself, the procedure will be more expensive. That's an interesting bit. That's why people usually, when they talk about selection sort or insertion sort, they talk about them together. So you will see exactly how they work in a different way. But it turns out their running time is just the same. But we'll talk about it. Yes, go ahead.
I understand that this can also be done recursively, and I was just wondering, would we ever get a recursive code and have to figure out
Okay, sure. I think selection sort, insertion sort, I think it makes more intuitive sense to do that iteratively because you can see exactly how the selection, things work. So if you do it iteratively, the steps correspond quite nicely to how you sketch visually. But if you do it recursively, I'm pretty sure it can be done, but it might be more complicated. So would you be given a task to really solve selection sort, insertion sort in a programming test? I guess not, because I wouldn't expect you to do that in 1 hour. I cannot do it, so I wouldn't expect you to do it, okay? But I would say if you want to take the challenge to do it, I would encourage you to do so, absolutely.
I would imagine it's much harder.
Much harder. Seriously, it's much harder, yeah. You don't really need to I would say another takeaway lesson, which we don't really say explicitly in this course, you don't really want to think, every time you want to implement an algorithm, you really got two choices, either iteratively or recursively. Which one to choose? Think about which one is more intuitive to your thinking and choose that one. Right? All right. For example, to calculate factorial, would you really have to do it recursively? Not really. If I were to do it, I might just do it iteratively. Usually when we talk about factorial for recursion, just as an illustration. But whether to do it iteratively or recursively, you got to decide. Okay? All right, that's about selection sort. Insertion sort, very quickly. All right? It's going to work the symmetric way, quickly. We're going to keep getting the first element as opposed to selecting the minimum. Now, you can immediately tell. If I always want to get the first element from some subarray, for example, I just want to get it from here, let's say. In that way, it's not expensive, just constant time. I'll always get certain index. Indexing from an array is always cheap. All right? Keep getting the first element from the unsorted portion, and then we want to insert it to the sorted portion, as opposed to just appending it to the end. You want to insert it into the sorted portion in a way that's going to keep it sorted still. That's something you want to keep in mind. All right? Let's see how that works. And to save some time, what I will do is, let's say we have this array here. Initially, let's say the sorted portion already got one element. It's not going to change the final answer, but just a little bit easier for us to think. Okay? Let's say we got this. And how do we run the very first iteration? Let's see. Right? So we're going to choose just the first one. Doesn't need to be the minimum. Just choose the first one. However, when you try to insert into this, you cannot just append it to the end. If you do that, it's going to be 3, 1. It's not sorted. You want to find out exactly where to insert. To find that out, you may need to take a look at the entire sorted portion, which is going to keep growing. So that's why the inserting operation will be cheap initially, but it will be more and more expensive as the sorted portion grows. That's the intuition you want to get. All right? All right, for this one here, we're going to, let's say here. So we're going to insert. So that will be at index 1, right? That's the first element. Insert A1. Okay? Insert A1. And then, what about the cost? Let's talk about the cost right away, too. In this case, in order for me to actually choose the first one here, just constant time, because I know that it's at index 1. And then, how do I insert? Insert over here, think about it more generally. This is a list with one element where I want to insert into the right place. It can be either before 3 or it can be after 3. So I need to consider, in the worst case, 2 possibilities, right? Insert will be, I would say, size 1. So here, when I say size 1, I mean, in general, it's a subarray of size 1 for insertion. Let's run maybe 1 or 2 more iterations. You will see more clearly. Okay? So in this case, we're going to have 1 should come before 3. So now we got exactly 2 elements in the sorted portion. And we got 4 and 2 remaining. 4 and 2 remaining. Right? Insertion sort. Right? For the first iteration. And what about the second iteration? Okay? For the second iteration, we're going to get another array over here. That one there. What should we select? What should we choose? What should we get? Well, exactly here, right? That's the first elements in the unsorted portion. Should be 4. So to go from here to here, we want to insert A2. What will be the cost? The cost over here, to really choose, is just about array indexing to get to these particular elements. It will be constant. What about the insert itself? That one there will be, well, now we are facing a subarray of size 2, right? You can see this size here is going to keep growing until we got n minus 1, where that's a final insertion, right? So this will be actually 2. Okay, let's say here we got 1, 2, 3 here, and then we got here 1. So now if you try to insert, how do I insert 4 into this particular portion to remain sorted? In this case, it should be inserted at the end. So there'll be 1, 3, and 4. Okay, and this will be the remaining one. All right, final iteration. So now, take a look. The final iteration here, we should really insert this element. Insert 8 at index 3 into the sorted portion over here. Now, think about in general. This will be the most expensive part for the insertion. This portion over here will be the last step. This, in general, will be just n minus 1. For the last iteration. All right, so now in this case, how do we insert 2 into this sorted portion so that it remains sorted? We have to insert somewhere over here. Exactly how this works, of course, you got to look at the Java code. But for now, just conceptually, you know what should be done. Right, so now it should be 1, 2, 3, and 4, right? So that is it is now completely sorted. What will be the cost for this particular iteration? For you to choose just this element here, it will still be 1. What about insert? In this case, you can see you're trying to insert into this collection here of size 3, which is n minus 1, right? Right, n minus 1. It is important to know. Question? Yeah. Briefly, yeah. Let's say this is what I select, right? Well, I shouldn't say select to confuse you. Let's say this is what I choose. Always the first element in the unsorted portion. Let's say I choose this one. Now I want to insert 2 into this particular array so that it remains sorted. If you look at the Java code, this is how roughly it's going to work. I compare 2 with the first element, go from left to right. This is less than that, so that means not here. And I compare 3 here. 3 is already greater than this. That means 2 should really come before 3. And then you got to do some shifting as well. All right, so that's why the insertion itself is not cheap. Yeah. Yes. Yes, indeed. If you look at the Java code, absolutely. There are many, there's quite a good number of other implementation details. But as you said, at this stage, as long as we talk about the critical steps, as long as we didn't overlook any step that's going to dominate the running time, we are fine. Yeah. All right. All right, let's now figure out the big O, right? It's going to be big O of, let's talk about choosing 1, 1, and 1. The number of iterations we're going to do will still be corresponding to the size of the array, right? So the number of iterations for inserting, you know what, for choosing. Will be n, right? This part here is the same as before, like in selection sort, right? If you remember what we did earlier, right? All right, so now let's talk about just the choosing part. 1, 1 for n times. N times 1. So this is choosing. choosing the first unsorted elements. Plus, and now what should be the pattern we should include over here? Right? Used to be the case n plus n minus 1 plus all the way to 1 for selection sort. Now for insertion sort, it's exactly the reverse. Because when we try to insert into the first, in the first iteration, the size of the sorted portion is only 1. For the second iteration, the size of the sorted portion is 2. And then all the way to n minus 1. So that's why it's going to keep growing. So the sequence here will be reverse. 1 plus 2 plus all the way to n minus 1. And let me change this a bit. And multiply by 1. Oh, you know what? Sorry. I think that's enough. Okay. All right, so this part here is just about the insertions. Right? If you do this addition here, or this summation here, it's the same, n squared. Right? So you can definitely try to simplify it. I'll let you do it. And then ultimately, the highest power will be, since when you do this sum here, it's going to be n squared, which will be higher than just n to the power of 1. So big O of n squared. Question? Yes. It's a very good question. I would say insertion sort, selection sort, normally, if you really want to do sorting for the serious purpose, you wouldn't choose either because they're quadratic. So I would say the ones we're going to talk about later after the reading week, quick sort, merge sort, and also heap sort, they will be much cheaper and log n. That's something we'll see. But I would say if your input size is not that huge, so n squared you can afford. So it doesn't matter which one you choose. Also depends on which one you feel easier to implement. Let's say if you want to implement by yourself. All right? Any question? So what we have done was we have intuitively sketched the two algorithms, and also we work out their running time. All right? And let me do a little bit more, and then we'll take a short break. This one here, just to summarize about the two sorts, right? I'll let you do any annotation you like. All right, so now let's do two quick exercises right now. So I got the Java code for you. I'll try to make it available to you as well. It's an Eclipse project. I'll do that. So the exercise we want to do now is to figure out the running time, okay, by doing the exercise we did last time, okay? And this one here, we've done that, so I can go rather quickly. Let's see, okay? It is a nested loop. You can see here, I will be 0 all the way to something like an n minus 2, pretty much like an n. And this one here, j will be equal to I, looks like a triangular pattern. Agree? All you want to look at is this part over here is going to be the body of the inner loop, which takes constant time, 1. And for each iteration of the for loop over here, the purple one over here, by the way, you can see there is some kind of swap. That's how you insert. Sorry, not insert. That's how you append in the case of selection sort, how you append. All right? Oh, sorry, append over here. All right, that's a swap. You can actually really, I'll give you some assigned task to do. All right, so the purple one is also 1. All right, let's look at the loop counter pattern very quickly. All right, if you think about I, value is going to be 0, 1, 2, 3, all the way to n minus 2. All right. What about the pattern for j? For j, it's going to be equal to I all the way to n minus 1. So when I is equal to 0, j will be from 0, 1, all the way to n minus 1. When I is equal to 1, it's going to be 1 all the way to n minus 1. When it is 2, it's going to be 2 all the way to n minus 2, and etc. What about the last iteration? It will be simply just n minus 2. right? That's a nice triangular shape that we did earlier. All right? Something like that. Okay? Are we okay with this? Right? We have done this already, right? And all we need to do now is to figure out how to organize the running time together. Okay? We'll do something very similar to last time. So let's say this. Big O of. How many iterations do we have for the outer loop? About n. From 0 all the way to n minus 2. It's basically n. But I can be more precise. From 0 to n minus 2. We got 0 and n minus 2. The size of that is n minus 2 minus 0 plus 1, which is n minus 1. All right? N minus 1 iteration for the outer loop. So that will be n minus 1. Okay, so this one here is the number of iterations of the outer loop. And we know that the purple part over here is going to take just 1. So I'm going to go back to purple. Multiply by just 1. All right? So this part here is line 3 and 6 to 8. All right? And we're going to combine with this part. What about the blue one over here? How many times the blue one is going to be executed depends on the number of combination between I and j, which is exactly over here. Right? That one there is going to be, let's see. How many numbers do we have over here? From 0 to n minus 1, n. From 1 to n minus 2. Right? What is that? n minus 2, right? I think I did something slightly wrong. Okay, I beg your pardon. Okay. You can see here it should be n minus 1, right? I think I should change that. Yeah, that's the mistake you definitely want to avoid. Don't be like me, all right? N minus 1, n minus 1, n minus 1, right? Over here, so that should be n minus 1. This would be n minus 2. All the way to just one number. All right? You got to add them up. It's going to be something like n plus n minus 1 plus all the way to 1. And how do you calculate this? The beginning plus the end multiplied by how many turns do we have? N turns. From 1 all the way to n. Times n divided by 2. All right? That's about how many combination of I and j. And times this particular part, which is 1. So 1 here is line number 5 over here. And this one over here is actually going to be the number of combinations of I and j. All right? And you can definitely try to simplify that into some term. Right? I put a question mark here because you got to fill in the blank. I'm pretty sure you can know how to simplify. Right? I'm going to leave that to you. In the test or exam, you cannot put question mark. All right? For now, I'm leaving that to you. But we can already tell. This part over here is going to be n squared, which will dominate linear. Right? So it's going to be big O of n squared. That will be the final answer. So now you see how important it is. Let me remake the point. It's so important. You could have waited until that you actually got a piece of code that's working, and then try to figure out the running time accordingly. Or, more valuably, even before you have to write a Java code, think about how the selection and sort work intuitively and work out the running time. Right? This is much more advanced than the Java code. All right? All right, any question about this? Are we okay? Question, please. Which one? Sorry, which one are you talking about? This one here? On the left. Oh, you mean here? Yes. You should go all the way from 0 to n minus 2. Yeah. So, but I agree. So here, I tell you what, even if I got another 1 or 2 iteration, it's not going to change the running time. Right? It depends on really how this is defined. Okay. Yes, n here, yes, indeed. Yes, let's clarify. So it's really important to know n here is this eta length. The size of the array, indeed. Yes. You can assume that n is passed correctly. You can assume. No, we wouldn't. No, we wouldn't miss any element. Don't worry. I think this code works. So that's why you want to do that important assignment I'll give to you at the end. Okay. If you're wondering about maybe this loop is missing some element for comparison, no, this is working. Okay. So exactly how this code works does not 100% correspond to what I told you intuitively. But if you got an intuitive idea, you shouldn't find it too difficult to understand this. Right? That's always, there will be some gap between intuitive working and also the code that works. Question? You can think of it, yes. That's something that was also, you see, in the case of insertion, so we didn't really start with like an empty sorted portion because a portion with only one element is automatically sorted. You can try to be a little bit more clever, try to be a little bit more efficient in some boundary cases, but asymptotically, they wouldn't change anything. So that's why for the coding, you always go for what really makes sense to you to make sure it is at least correct, and then you worry about efficiency. Okay. Alrighty, for insertion sort, it's going to be something very similar. How about exercise for you? All right. And I'll try to write down some solution for you at some point, but you definitely want to do it. Don't wait for my solution. All right, so you should really follow a similar procedure as I did over here, and also based on what we learned last lecture. So you should be able to do this. All right. Any questions about this so far? All right, so what should you do beyond this case study? Let's do some very quick conclusion, and then I'll give you a short break, and then we'll start linked list. Okay? Alrighty, so selection sort, we talk about it. Insertion sort, we talk about it. And so this is just about summary about how these two sorting algorithms work intuitively. And the exercise, you can try to look at the Eclipse code I'm going to make available to you. You can try to make some modification. For example, let's say you try to sort maybe in the non-ascending order rather than ascending. Right? You can try that and see how things should be modified. And also, you can see here in our case, the sorted portion is always on the left, from left to right, from left to right, from left to right. What if I just change the color from red to green, green to red? That means the sorted portion should be starting from here and grow all the way to the left. If I want to make that modification, how should you change the code accordingly? Of course, the asymptotic upper bound will remain the same. Now the question is, how can you change it programmatically? That's a nice challenge for you. All right? Think about it. All right, so this is an important task for you to do. Given a fragment of Java code, you're expected to, number one, you want to derive its asymptotic upper bound, which we did, without even knowing its logic. Number two, you want to trace its runtime execution. This is something I will ask you to do beyond the class for your learning. We did one already, and we discussed how intuitively the two sorting algorithms work and work out their running time. We tried both, either based on the intuitive sketch and also based on the Java code. All right. And we're now going to trace the Java code on paper on our own. How do you do that? So I would suggest you try to take a look at the clean pages I provide to you. Right, so that will be selection sort. And to trace, you ought to see when I keeps growing, what's going to be the corresponding states of each column over here. Think about it. For example, what should be the value of I, and what should be the corresponding value for j, and what should be the minimum index in this particular code. And also, after the execution for each iteration, what should the array look like? All right, that's something you guys should really figure out. And try to figure out just a few iterations, and you will really appreciate how things work so effectively. And I would suggest if you really struggle with this, that's okay. I do have some videos to help you if you want to spend some time. All right, all these. And especially for the number 3, that one shows to you how you can use the debugger in Eclipse to actually trace the algorithm. If you don't know how to use debugger, again, that will be your chance to learn about it. All right, and then finally, a selection sort, insertion sort, asymptotically, they're the same. Doesn't matter which one you choose. And we'll learn about n log n, merge sort, quick sort, and heap sort. These are the other 3 we're going to learn after the reading week. They are more efficient. At the same time, they're more complicated. All right, that's something we'll do later. Okay, let's now take a short break by taking attendance. All right. All right, please check in. If you got any issue, please come forward right away. All right, I got a sign-up sheet for you as usual. All right, do it now, please, and then I'm going to close it. All right? All right, done. Guys, take a 2-minute break, and then we'll continue with the linked list. All right? All right, if you got any trouble, please come forward right away. Trouble?
Yeah, it's like the second time. I don't know why.
Yeah, I'm not sure. Okay, did you enable your data plan? You mean like a location service there? Well, you can try next time. Yeah, just sign up first,
Okay.
please. Trouble?
How do I enable the location?
I think, yeah, iPhone, right? If you don't
Yes.
mind. Okay. I believe if you just, oh, actually you did already. Okay.
Yeah, I turned on my internet.
You know, I'm not too sure. Maybe drop by at some point in my office hour. We can do experiments. Yeah, but I don't mind if you sign up.
Yeah.
Hopefully not every time, right?
Yeah.
All right. Do you have a pen?
Today I won't be.
Oh, can he use your pen maybe? Yeah.
I have an appointment at 3:30, so I can't go to today.
That's okay. We'll do it later. Yeah.
Are you have also tomorrow?
Tomorrow too. Yes. Did you sign? Did you check? Yeah. Can you put a check mark, please? Okay. Yeah, go ahead. Thank you. Not working for you?
I got it and it just...
Yeah, try your mobile device next time, please. Okay. Find your name here, and then... Thank you. Okay. Do you have a pen for yourself?
no.
All right. Oh, actually, could you please sign here? Yeah.
Oh.
Do you have a pen? Do you have a pen? Oh, maybe, sorry, can you use yours too? Yeah, sorted by last name. If you put a check mark besides your name. All right. All right. Ask me again, maybe after class. I'll give you proper attention, yeah. Also, having trouble? Yeah, if you can find your name, maybe use a pen from your classmate, right? I'll have one, all right? How was it? Was okay? Okay, very good. All right, guys, we'll resume in about 1 minute. Okay. Hi. Are you listening to in my class?
Pardon?
Are you listening to music in my class?
Right at this moment, no.
No,
I just keep them in.
no, because I thought you put it on, right? I'll be grateful if you don't.
Okay.
Appreciate
Sorry.
it. Thank you. No problem. Yes, please.
When I first logged into the attendance, I had to try it with my phone after my computer said I wasn't physically here, so I missed the poll card
From when?
today.
From today, right?
Yeah.
Okay, why don't you sign out quickly? Okay?
Okay.
Yeah.
Let me just
Go.
go.
All right, we'll start very soon.
It's not really important, but the TAs made just a small typo, and I assume it's the TAs who made in there's 5 ways to count something when they meant 7. Like they even listed 7, but
Which part?
it's in like task 3 and 4, the one where it's the ways to climb the stairs. They say there's 5 ways to climb when there's.
Oh, if you don't mind, would you mind pointing out the typo to me? I can fix it.
Okay.
Yeah,
Sure.
I appreciate that.
It's not really important.
Yeah, no problem. You know, I'm more than happy to fix it. Thank you. I appreciate it. Thank you. All right, guys, let's now get started again. Yeah, we got about 20 minutes, and let's see what we can do. Yeah, if you got any issue with your location service, maybe try to fix it if possible. Yeah, but I don't mind bringing the sign-up sheet, but you can save some time for everybody. Okay, let me exit from there. Linked list. Okay, what I would like to do is, before this, I would like to give you guys some very general remark about the linked list. This will turn out to be a very useful topic, especially for those of you who might have to do programming interview later, either for your co-op, maybe for your job. I think a very common category of problems they'll give to you is to do some utility method by linked list. That's something I'll also give you guys a chance to practice in both the assignments and also in the programming test. I think you need both. But I really, really encourage you to try some extra resources. I'll give you one example. Have you guys heard about LeetCode before? Maybe? Okay. It doesn't need to be LeetCode. I believe these days they got tons of interview preparation websites. I believe many of them you may have to pay. I'm not saying you have to pay for them. There are many others, they might just be free to some extent. For LeetCode, I stopped my subscription for a few years already. So I believe I can still get access to some problems. I'll show you how you can find them. So again, doesn't need to be LeetCode. Any website that's meant to prepare you for interviews, they might just be applicable. I'll show it to you. Let's say you go to leetcode.com and then select problems. And then once you get there, you can see expand over here to see the topics. Linked list. So what you will typically see is like this. Let's let it load. Right, they got like a problem, medium, easy, hard, and etc. Right. Of course, after today's lecture, or maybe next Monday's lecture, you will be able to start doing the easy ones. I'll give you just enough so you can start working on that. So these are all the problems you can do. I'm not too sure if you don't have a subscription, maybe they wouldn't allow you to submit a solution for evaluation, but at least you can try all the problems and write some JUnit test cases for yourself and do more. Sometimes I might get some inspiration from the LeetCode problem over here. I wouldn't give you exactly the same. Maybe I'll try to, sometimes I need to simplify that a bit. I cannot, you only got about 1 hour for programming test. I wouldn't expect that much. But it'll be a very nice practice for you, not just for this course. Yes? Yeah, thank you, thank you. Yeah, so your classmate just verified, you can still submit it for some feedback, even without subscription. That's good news for you, yes. Larry, oh, I see. Am I going to give you a hard problem in the programming test? Probably not. However, let's say this. I try to really judge whether it's going to be reasonable to solve within 1 hour, right? So I can tell you sometimes you might find what they label as hard is not really hard. And sometimes you find that the label as medium or even easy is actually harder, right? So don't worry, I think I'll be reasonable. I know that you only got 1 hour, so I'll be reasonable. Yeah. That's another issue. All right? That's a resource that you can definitely consider. Right? If you find any good site you think that your classmate can benefit, forward it to me. I will share with everybody. All right? That's something you guys can also do. Maybe send a link to me. I'll share with everybody. Thank you. All right, singly linked list. So today, maybe we wouldn't be able to touch the programming part. Let's now clarify some concept about it, and then we'll see some Java code next time. All right, how about that? We got about 14 minutes, okay? No more, no less. Singly linked list. So we know up to now, arrays perform pretty well if that's about indexing, but pretty bad if you try to do insertion and deletion, especially the insertion example we did, right? It's going to be linear. Keep that in mind. So for linked list, as we go through the various operations you might do on a linked list, you want to always compare, think to yourself, what if I want to do the counterpart in arrays? It's going to be asymptotically more efficient, less efficient, or equally efficient. Always keep that in mind. Okay, let's take a look. And we're going to introduce an alternative data structure to arrays, and it's called a linked list. Right? Let's be very careful about this sentence over here. A linked list is a series of connected nodes. What do we use for connection? The answer is reference, like what you learned in OOP in 2030. And forming a linear sequence, I'll explain this in a moment. And at the runtime, no connections are through reference aliasing. Okay, let's see exactly what I mean here. Okay, for today, I just want to give you some intuitive idea about linked lists. But the number of challenges it can be generated from there is infinite. That's why usually people like to give you challenging problems in the interview on linked list, not arrays. Arrays are pretty much boring, right? It's not that interesting, okay? Right, so first point is, when we say singly linked list, I'm going to visualize that to you right away. It's a chain of connected nodes, okay? And the most intuitive way, this is how you can think of. This will be how we can visualize a node. Think about this is a node. And there are two parts of the node. And you can think about there will be two references in general. One reference will be to the data. Maybe you want to store strings in your linked list. In that case, the data will be a string. Maybe you want to store a linked list of persons, a linked list of trees, a linked list of bank account, whatever, right? That's the data. The next one might be new to you. It's called the next reference. What does that mean? That means if somehow I got access to this particular node, if I want to go to some later nodes that's connected, I have to first go to the next one, and then from there I can go to the next one. That's the nature of linked list. Let me draw a little bit more to show to you. Let's say we got another one here. Let's say for this part over here, this will be, again, the data. And we also got the next. Let me just draw one more, and I'll illustrate some points to you. And over here, there will be some data and also some next. So there are two cases for the next reference, as you can see. Case number one, if you look at these two next, let me just make some reference here. So, and we typically say the very first node, we call it a head. I'll speak about how you can implement this in Java, maybe next week. Call this the head. So now if I do head, which is referring to this, head.data is going to tell you what data it is. Maybe a string, maybe a bank account, and etc. Okay? If I say head.next, That one is going to give me the reference of this particular node, right? Let's write down. So here we got head. It is referring to the first node. If I say head dot next, that would be the second node. What about the third node? Head dot next, right? Third node. All right, let's try something similar. Let's say we're storing string. Alan, Mark, and Tom. So these are the data, right? Let's try that. If I got, let's say, head dot data, that should really give back to you Alan. Agree? Head dot data give you Alan. And if I say head dot next dot data, in that way, head dot next dot data, which will give me Mark. One more. If I say head dot next dot data, you can see this part over here is the same as this part over here. It's referring to the third node, which is over here. And dot data again is going to give you Tom. And I'm going to write another thing for you. You tell me what's going to happen. Okay? What about this one here? If I say head dot next dot next dot next versus if I say head dot next dot next dot next dot data. Number one here, number two here. For number one, if I run it in Java, what's going to happen?
It's going to be like null because it doesn't point to anything.
Null, not error, null. Okay, it's really important. Okay, let's try. For number one, 3 next. Head, next, next, and next. No node. It's a reference, so by default, null value. Okay? And people like to draw in this way if that's null. They simply say like that. So that means it's a null. That usually marks the end of the list, of the chain. But you never know how many nodes there might be from the current node. All you can do is, from here, I can go to the next. And then I may have to go to the next. I may have to go to the next until I reach the null. Then I will know I'm now at the end of the chain. Question? Not yet, not yet. You're thinking ahead, which is good, okay? Let's talk about number two. So for number one, the output is actually going to be just null, all right? What about number two? Head dot next dot next dot next dot data. What are we going to get? Depends on the data. Are you sure? We already got Alan, Mark, and Tom. Is there any data in our visualization? Null pointer exception. Because, let's be careful here. Head, 3 next, and the data, right? Head, next, next, next. Up to here, it is a null. Data, null pointer exception. All right, let me write it down. I'll make some remark. Up to this point over here, it is null. And whenever you're trying to invoke any attributes or method on a null reference, it's a null pointer exception. Why am I talking about this? Don't worry, I'm 100% sure you'll run into this, either in the assignment and or your programming test. This is the number one most frequent mistake you can run into when you manipulate in the linked list, because you thought there is certain node that's being pointed to, so you can inquire the data, but it may not be. Right? That's something you really have to understand the principle to know why it happens, and then you got to make sure you program in a disciplined way to avoid it. But again, even for, I'm not a very good programmer, but I run into it also very often. So I'm saying that you got to be very careful. The more important thing is, if you really run into null pointer exception when you program in linked list, you ought to know how to use the debugger to fix it. Right? That's a critical thing. That's why learning how to use debugger is so critical. All right? Are we okay so far? Okay. Another terminology I would like to talk about, linear. Okay? For the linear over here, so linear means whenever you got some position in the chain, you got a single unique next reference. That's called linear. Okay? Linear means each node has a unique successor. I briefly mentioned about this in the syllabus walkthrough session before, but it's more like a reinforcement. That's a linear. And is array linear as well? Indeed, right? If you think about an array, if I go to any index over here, let's say, is there any just one unique successor? So array is also linear. So both the array and the linked list, they're both linear structure. One will be nonlinear, when a single position can have two different successors. In that way, it will be a nonlinear structure, which we'll need to touch when we talk about trees. All right? We've got about 3 minutes. Let me just try to use up your time, if I may. So each node in a singly linked list, as I said before, reference to some data objects and reference to the next node. Right? Now you see how it works graphically. And we're going to see exactly how to implement this on next Monday. I'm going to make the slides is already there. I will encourage you, if you want to study ahead, feel free. That might help too. All right, that's, okay, relative positioning. Relative positioning simply means typically what you will be given is only some arbitrary node in the list. And then typically maybe the head. And all you can do is to go to the next one or go to the next one. It would be very expensive if you want to go absolute indexing. Okay? So this is also a very critical point.
Absolute indexing is constant number, so isn't that like
Yeah. I'll just write it down. Okay. Relative positioning over here. Accessing a node. You know what? This one requires a little bit more detail. Let me just put a star. I'll continue from here. But let me skip this part just for that. Sorry. That's a little bit detail. I need to spend a little bit more time on that. Let me see the next one. And then, okay, so let's go over this bullet point and then we are done for today. The last node in a singly linked list is different from others. We already covered this. If you look at that, here, this will be the last node. How is that different from all the previous nodes? Exactly. The next reference over here is null, whereas the next here and the next here, they are not null. You want to think about over here, if you try to say head, it is not equal to null. It is true. Head dot next, not equal to null is also true. Head dot next, not equal to null is also true. But if you say head dot next, it will be equal to null. Right? So play with these expressions. All right. Okay, I think I will stop here and then we'll continue. Okay, next Monday, there's no lecture, right? We got your written test. Show up in the designated place in Williams Small Center. Please make sure you check your login. And then I will let you know what to do with the missing time for the class. Don't worry.